following program is brought to you by Caltech.
So next up is Chris Harada, who's from here at Caltech and probably needs no introduction to everyone here. And we're going to continue our trend down the redshift line a bit and work our way into the dark ages and the molecular and atomic features that are in the CMB and imprinted on the CMB in the radio from that era. So as soon as Chris gets hooked up. So Chris is a faculty member here at Caltech. He has been working for quite extensively on atomic lines and a number of other theory projects in the Taper group. And you were an undergrad here as well, correct?
That's correct.
You tell me, I don't know where you were a grad student.
Princeton.
Princeton, okay.
I decided to come back.
And Chris was brave and came back to the warm West Coast weather. Okay, all right.
Okay, can everyone hear me? All right. So I was talking to Steve Furlanetto, and we were deciding how to break up the presentation. And the agreement was that Steve was going to cover the hydrogen 21 centimeter line. And as you can see, my job is to cover everything else in the early universe. There's a lot. I can't literally do everything. But what I thought I would focus on is first what happens after the recombination epoch, how are the first molecules in the universe made. And then I'll say just a little bit about a couple slides on the cooling and the formation of the first stars. And then I'll spend the last part of the talk talking about metal scattering lines, which of course you'll only see after the first stars because somebody has to make the metals. Everything I'm going to talk about is going to be hard to detect. None of it has been seen yet. And that's why we're here. So when we get into that regime, the regime where none of this has been seen yet, there are really two types of approaches one can take. The things I'll talk about in this talk contain some elements of both of these approaches. One can approach the dark ages from either direction. One can treat it as a sort of forward calculation problem, a physics problem, where you say, we know something about the initial conditions of the universe, adiabatic CDM plus baryons plus photons and neutrinos. This has actually been a very successful approach for the microwave background anisotropies, because it's just perturbation theory. It's nice. It's a first principles calculation, which to a physicist like me is appealing. Unfortunately, there's a flip side to this type of thing, which is that the uncertainties multiply at each stage. Each sequence in the calculation, because you're taking these initial conditions and working forward and working into different physical regimes, each sequence in the calculation gets harder. The uncertainties multiply. If you do something wrong at one stage, you may or may not know. So I'll show you one example, a sort of cautionary tale, actually from the formation of the first H2 molecules, where we actually were missing something for several decades. The other type of approach is to think of this from an astrophysical perspective. And when we start talking about the first metals, that's really what you have to do. You take some guesses as to how the baryons behave in very high redshift galaxies. Then you put together some sort of model, hopefully calibrated to lower redshift observations, Then you make some plots and hand them to our observers who either tell you they think they could see that or not. All right, so I'll start with the sort of forward calculation approach. So we just heard a very nice talk from Jens about the recombination epoch, during which the three elements produced in Big Bang nucleosynthesis go from being fully ionized to either neutral or partially neutral. The lithium doesn't actually recombine in the recent calculations we've done. It remains as lithium-2, which is unfortunate because lithium-1 has a nice resonance line in the red, but lithium-2 is electromagnetically inert. And then this, of course, occurred because the temperature dropped so that kT is equal to the ionization energies of these elements divided by some large logarithmic factor. But what happens next? Well, as the universe continues to expand and cool, you know, thermodynamically, it would be favorable for the hydrogen to turn into molecules. And so how should that work? Well, in order to understand how that's going to work, we have to talk a little bit about what does and does not happen at the end of recombination. Recombination is a second-order reaction. It requires a proton to meet an electron, and therefore the reaction rate here is the conversion to neutral hydrogen with the emission of some number of photons is proportional to density squared. You can see that here. And these reactions, if you think back to your introductory chemistry class and what second-order reactions do, the abundance of the reactants actually goes down as a power law instead of an exponential. It goes as 1 over t. Here, the rate is varying with time, so it's a little bit different. But the end result is that you get a freeze-out at a non-trivial electron fraction of order 10 to the minus 4. And that's a very small density compared to the density of photons or even the density of baryons. But it's enough to play a key role in the formation of H2. OK, so and then the lines that we would talk about from this epoch, the hyperfine lines I'm not going to talk about. The hydrogen recombination lines Ian's already talked about. And then the other possibility is the molecular lines. In particular, H2. That's pretty much all you can make out of hydrogen and helium. So this is really going to be the focus for the first half of the talk. OK, so enough prelude. How do we actually make hydrogen molecules? Well, the obvious way to do this is to take two hydrogen atoms and put them together. That's thermodynamically favorable at redshifts below a few hundred, but there's no dipole moment for that reaction. The hydrogen atoms are symmetrical. So that reaction isn't going to go anywhere. You might next imagine that there's this huge bath of photons. You could take two hydrogen atoms and a photon and put them together and make an excited H2 molecule in an excited electronic state that has odd parity, and hence this is dipole allowed. And then it could decay back to the ground electronic state of the H2 molecule. You'll recognize this type of process is actually the inverse of H2 photodissociation. And indeed, if you went early in the recombination epoch, when the universe is still in something resembling equilibrium, you put a few hydrogen atoms in there. This actually establishes an equilibrium abundance of H2. Of course, that equilibrium abundance is tiny. And as hydrogen recombination proceeds and a spectral distortion builds up, there are all of those Lyman alpha photons and so on. This reaction, well, it's not obvious which direction it's going to go because there's a UV photon on each side. But Esfandiar, who's a visiting student here, actually did that calculation. We're working on writing it up. And the answer is you don't produce any significant amount of H2. So that's not going to make very much in the way of early molecules. What about using the non-trivial ionization fraction? Well, this is much more promising. And it was actually the first mechanism proposed to make primordial H2. So how does this work? The mechanism is down here. You have a hydrogen atom and a proton. And it turns out there's a dipole moment to bind those two because it's not symmetrical. You can make an H2 plus ion. That's weakly bound, and you can go either direction. That's part of the problem. But sometimes this H2 plus ion will run into a hydrogen atom first, and then you'll get a charge transfer reaction and make H2. Shortly after that was proposed in the 60s, there was another mechanism suggested using the electrons instead of the protons to do basically the same thing, where you can attach an electron to a hydrogen and make the well-known H- ion, which has a binding energy of something like 3/4 of an eV. And once the microwave background has redshifted to less than 3/4 of an eV, which happens around redshift 100, the H- ions are no longer going to be photodetached, but instead start to react with the neutral hydrogen that's present, and you can produce H2 this way. And finally, you imagine at very high densities, meaning only in collapsed virialized objects that may form the first stars, not in the general IgM, you could get three-body reactions, which are purely collisional. But something like this happening at intergalactic densities you can neglect. OK, so I told you that this kind of forward theorizing was dangerous, and I'll just give you one example of why. For a paper I had with Nikhil Pavnanabhan about 4 years ago. So this paper was about screwing up the formation of H2 because of the non-equilibrium populations of the rotation vibration levels of H2 plus, which sounds like a fairly technical thing, but I'll show you in a couple slides how much of a difference it makes. So the idea here is that the positive catalytic channel, the H2 plus channel, was believed at one time to contribute most of the molecular hydrogen formation at redshifts above about 100. And what's wrong with this? Well, what's wrong with this, we have to understand to understand this, we have to look at the energy level structure of this ion. So H2 plus has a single electron, and it can either be in a symmetric or G or the antisymmetric U orbital around those two protons. And I've drawn here the potential energy curves for both of those symmetries. The ground state, ground electronic state, has a minimum at a separation of 2 Bohr radii, about an angstrom, and a binding energy of 2.5 eV, a little more, 2.6, something like that. That's the traditional H2 plus that we usually think about. The unbound, the antisymmetric state is unbound, except for van der Waals well way out here that I won't concern myself with at the moment. So that's a repulsive potential. Now, when an H and an H plus approach each other, they approach each other in some superposition of these states. Only the U state can decay to a G state by dipole selection rules. And so its wave function, the wave function of the incoming unbound molecule, is restricted to large radii. The wave function of the bound molecule is restricted to small radii. And you know from overlap considerations, this is going to mean that the radiative decay rate is very small, except to these very, very high energy, very weakly bound levels of H2+. And so the consequence is that the formation of H2+ goes almost exclusively to these very high-lying states. The C and B can relatively easily dissociate those states through dipole-allowed transitions. The decays down to the ground state are forbidden. They occur only by electric quadrupole transitions, which are much, much slower because the wavelength is much longer than the size of the molecule. And so the consequence is that the formation of H2+ in its more stable ground state is suppressed. In fact, it's suppressed so much that the primary mechanism by which you produce H2+ down here is actually another catalytic channel involving helium. This is the only instance I know of in which you get a helium-catalyzed reaction of any significance. But the point is that that even this is relatively small, and the production of H2+ down here is slow. There are the level populations. So you can see the thermal equilibrium level populations as a function of the energy of those levels. And you see what you get is wildly out of equilibrium. This is a generic feature of H2+ in astrophysical environments. And here's the molecular hydrogen abundance calculation that you get out of that as a function of redshift. These are, you can see what kinds of changes are made, orders of magnitude change in the H2 abundance. It's not clear how significant all of that is going to be in the long run, because H2 will also be produced again in the halos that form the first stars. Nevertheless, the fact that something like this is going on and escaped the attention of theorists for 40 years, despite the large amount of work that's gone into cosmology, should give you some caution about everything else I'm going to tell you in the talk, including this plot. All right, so the first stars. When a halo forms, the first dark matter structures form, and then the larger ones form, and then eventually things above the baryonic genes mass form, then you start producing more H2 in those halos because you have this negative catalytic channel that's going on. And it's quite efficient because by this time the microwave background has redshifted way out of the regime in which it can destroy H-, and the densities are high enough that these reactions can proceed. If the temperature of that halo is high enough to start exciting H2 rotation lines, then the halo is going to cool. The baryons will radiate away some energy. And when they radiate away energy, they'll collapse, the density will go up, the cooling rates will go up, and so on and so forth. And eventually, you can make a little molecular cloud, and eventually, you could imagine forming a star. And many, many papers have been written about this, both analytical and in simulations. But you might imagine, well, the H2 rotation lines that you're producing, the 28 and 16 micron lines, at maybe redshifts of order 30, are now redshifted into the submillimeter and millimeter. Can we look for them? Unfortunately, this is going to be really hard. And the reason is that if you think about just the cooling that leads to the formation of the first stars, it's hard to see how you get more than an EV of molecular hydrogen radiation per baryon out of this. Because if the energy source is gravitational and the system is virialized, then after you radiate away that much energy, your temperature gets high enough that you're going to start exciting other lines. You may destroy H2. You may switch to Lyman alpha cooling. Lots of things you can imagine. But you're not going to be radiating more molecular hydrogen rotation lines once you get above that temperature. So the number of photons per baryon involved is only squiggly 20. And the fraction of the baryons participating in the formation of the first stars is tiny. I'm not sure what fraction or how many stars formed in this undisturbed primordial star formation mode. But whatever it was a minuscule fraction of the baryons. That much is clear, at the very least, from the integrated star formation histories at high redshift, and also the fact that there are metals and so on. So you know that the fraction of baryons that were in this undisturbed star formation mode must have been small. And so if you're dealing in the regime where there's substantially less than 1 photon per baryon, then that makes it harder than these primordial recombination lines that Jens was talking about. And we haven't seen those yet, and it's a long road to get there. So I think this is, if it's ever going to be possible, is a very, very far future thing. You might then think about fluctuations in the, from these primordial star-forming clouds. We talked about the isotropic background. There are also fluctuations. But once again, the number of photons involved is small compared to those involved in the foregrounds, which are all the other mid-infrared lines from somewhat lower redshift. So I think the bottom line is if we're going to see high, the very high redshift H2 lines, it's probably not, at least the first such things we see are probably not going to be from the release of gravitational binding energy from those first objects, unfortunately. All right, in my remaining time, I'd like to talk about metal scattering features. So once you have the first generation of stars and you've polluted the intergalactic medium with some metals, carbon, nitrogen, oxygen, silicon, sulfur, and so on, you can then start imagining that the magnetic dipole transitions, the fine structure transitions of those metals, will start scattering the CMB. They're in approximately the right frequency range. They're tens to hundreds of microns wavelength. And they're at, and if this is at redshifts of order 10 or 20, this is actually a good place to be to scatter the CMB. Unfortunately, these are magnetic dipole transitions. So you've got another factor of alpha squared relative to the well-known electric dipole transitions. So even if the abundances of these things were comparable to that of hydrogen, and in reality they're 10 to the 4, 10 to the 5, whatever less, you would expect to see an optical depth that's much less than for Lyman alpha. Nevertheless, with some precision CMB observations, maybe you could go after them. And that was the idea behind this paper. That came out when I was a graduate student at Princeton, and the ACT collaboration briefly got excited about this and then got down to the practical work of building and calibrating detectors and realized that this was really, really hard. So what are we looking at here? Well, the optical depth to scattering in these lines is small. If the metal abundances are of order 10 to the -6, which is a reasonable guess for the intergalactic medium at pretty high redshifts, then the optical depths come out of order 10 to the -5. The effect of this on the CMB is similar to what reionization does. It appears at about the same time. It has a lower optical depth, except that it's frequency dependent. It's a line. It's not a uniform distribution of electrons. So what could you do with that? Well, you could look for variations in the power spectrum as a function of frequency. There's no cosmic variance limit in that because the CMB itself is frequency independent. But when you start thinking about this, the first thing that comes to your mind is foregrounds. And the second thing that comes to your mind is that the slight variation of the CMB fluctuation amplitude as a function of frequency is precisely what you will get if your frequency-dependent beam model has a small 10 to the minus 5 error. So that's a bit of a worry. What might this look like? So I pulled one of the plots from this paper. These are two different ionization histories. This is as a function of the observation frequency, the change in the CMB power spectrum due to these metal scattering features. You can see here at the low frequencies, you're looking for scattering features that have not redshifted down to that frequency yet. Right? This is for a given species, say carbon-2 here. This is low redshift. This is high redshift. In some cases, some of these, the oxygen-3, the nitrogen-2, have multiple lines. So you're actually seeing here the superposition of two different features. And of course, the only thing that would be measurable is the total. So if you were to observe something like this, what you'd be seeing is some combination of the metal enrichment history of the IgM, the ionization history, and the mix of metals is all superposed. So it could be an interesting job disentangling that. How might one disentangle it? Well, sort of three ideas come to mind. The original idea from Basu et al. Paper was to correlate the temperature of the CMB with the temperature differences, and that's proportional to the optical depth in these lines. A second thing you might imagine is, I said it's like reionization, so you'll produce E-mode polarization at the low multipoles. And that E-mode polarization will then depend on frequency in basically the same way as the plot I showed earlier. That's another way to do it, but low L E-mode is already a pretty difficult business in terms of foregrounds. And it's going to get even more difficult if one starts talking about these tiny fluctuations that are small compared to the CMB itself. And finally, a third thing that I haven't seen mentioned, but I'm hoping that in an interdisciplinary workshop like this we can start talking about, is what you could do if you had not just frequency dependent CMB maps, but also 21 centimeter, because then you could start imagining cross correlations. Right? You could design a template for this polarization that includes not just the CMB polarization, but also a correction, a modulation in each little cell in three-dimensional space from the 21 centimeter signal. And if you do that, then that modulated signal has all kinds of small-scale structure in both the frequency and the angular dimensions. If you use that as a template to try to pull it out of millimeter wave maps, maybe you could start to get below some of the foregrounds. Also, because this is frequency specific, it would have the advantage of actually separating the contributions from all of those different metal ions. So you might learn a lot more if you saw that. There are, however, foregrounds to all of this. And the one that one first thinks of actually is that we know in the low frequency sky, at frequencies less than 1.4 gigahertz, the sky is supposed to be a three-dimensional map of the H1. There are several people in this room who are working on looking at that. The high frequency sky, if you go to the millimeter range, should contain similar maps, all of the carbon to the CO lines, all of those lines are making 3D maps on the sky. And if you do the sort of diffuse emission thing, they're all superposed. So in principle, you could imagine that as another way to do large-scale structure, at least statistically through cross-correlations. You can separate the contributions of different lines. But it's also a foreground for this metal scattering business. And here's a model of these things. This was based on, it's a fairly simple model. It was based on taking line ratios from redshift 2 to 4 galaxies and filling the universe with things with those line ratios. But what you can see is that you're talking about temperatures, mean temperatures of order of microkelvin, and fluctuations that rise to the level of order 10 to the -3 of the primordial fluctuations if you were to take a narrow frequency channel. And the concern, of course, is that the metal scattering features we were talking about are down here. So just to conclude, I've talked about a whole bunch of ways that one might get lines out of the early universe that are not H1. Unfortunately, the signals are, in every case, weak. Possibly undetectable, certainly hard. Some of them are correlated with the microwave background. So any sort of relative calibration, beam matching issues, the same things we worry about in 21 centimeter to get rid of the smooth galactic foreground, all of these things are going to come back if we try to look for those signals, especially the metal scattering lines. The foregrounds are brighter than the signal, and so some combination of intelligent ideas are going to be required to pull them out. And some of them have frequency-dependent structure. So the question that I hope we start to answer at this workshop is which, if any, combinations of going after these things are likely to be possible.
This program is brought to you by Caltech. Visit us at caltech.edu.